notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos, sections 1, 2, and 3, 33 videos and 12 more and 6 more. All of those 51 videos have been published in their entirety on YouTube. Please make good use of them. Section 4, measurement. All 17 of these videos have been completed, but only 5 are published in their entirety on YouTube. Section 5, statistics. We are now here. This is the 11th of 17 videos, and I am far behind schedule. Section 6, algebra. Then section 7, relations, functions, and graphs. Section 8, geometry and trigonometry. And section 9, vectors and matrices. This is no longer valid. This schedule was just a projection which now has to be adjusted. A reminder that I have divided section 1, number theory and computation, into 33 videos, and they are all available on YouTube in their entirety, as I said. And that is because this section forms the foundation on which the rest of the syllabus is based. So these 33 videos here, please make good use of them. Another reminder, you need to know the times tables from 2 to 12. If you already know them, fine. If not, you will have to learn them, especially since calculators are not allowed in paper 1. From section 2, all 12 videos are published in their entirety on YouTube, as I said. From section 3, sets, all of those 6 videos are published on YouTube in their entirety. And section 4, measurement. There are 17 videos in this section. These 5 that you see here, highlighted in yellow, are published on YouTube in their entirety, and these others are only partially published. We are now on section 5, statistics. Before we go on, recall I said in the introductory video that you will need a good math textbook or a set of 2 to get more practice questions. CSEC recommends the following, shown at right. These textbooks here. From that list, pay close attention to these last 2 here, since they form a very good 2-volume set of math textbooks that is quite adequate for the current CSEC math exam. This is a picture of volume 1, Mathematics, a complete course with CXC questions by Raymond Tulsi. And this is a picture of volume 2. Disclaimer, I get no financial or other benefits from the sale of these books. Also, very recently, late 2024, a website with AI interactivity has been made available free of cost that deals with past CSEC math questions only. That is from paper 2. You can navigate by topics or years, where all questions for the past several years have been worked out. If you have a question that you need explained, you can ask the AI assistant either by text or voice, and most likely it will be explained to you. It is extremely important that you become familiar with how CSEC sets its questions for paper 2 mathematics and what will be considered good answers to such questions. The URL for that website is shown here, RSC student. On the next slide, I will show you what the home page looks like. So this that you see here is the home page. You will have to register first and subsequent to that, sign in. This is the URL again. This URL will be in the description of this video below, so you can easily click on it and be redirected to this website. A reminder that you will be provided with a formula sheet for the examination, which looks like what you see here on the left. There will be a link in the description below from where this formula sheet can be downloaded. Of course, if you have the syllabus, this formula sheet is in the syllabus. Keep in mind that you do not need to memorize these formulae on this formula sheet, as the sheet will be given to you during the exam. Here is a top part of that formula sheet so you could see it more closely. And while you don't have to memorize these formulae, you do need to know when and how to use them. And this is the below part of that same formula sheet. As I said, you do need to know how and when to use them, even though you don't have to memorize them. So we are at statistics. This is a print screen for the first 5 objectives, which we have covered in 7 videos. Since this objective here required 2 videos, and this next objective here required 2 videos. Then we completed this objective 6 here, video 8 in this section. We completed objective 7 in 2 videos, video 9 and 10 from this section. So we are really here at objective 8, which is the 11th video in this section. After that, we have to do some more objectives up to 14. So section 5, statistics, has 14 objectives. I have divided those 14 objectives into 17 videos, as you see here. And so far, we are at this point here, where that red line is. Those 3 have been completed and published in their entirety on YouTube. And these others that you see here, up to here, are partially published on YouTube. As I said, we are here, objective 5.8, video 11. Once that is finished, it will be totally published on YouTube. Just another reminder that this section is of particular interest and importance, as you will have to make use of many of these concepts and principles in your SBAs. Especially if you are doing physics, you have to do similar profile, which involves analysis and interpretation for SBA. So you have to collect data, you have to analyze that data, often using a graph, line graph or otherwise, and then interpret that graph, extracting information from the graph. You may also have to do projection. As a matter of fact, projection is required. And this doesn't only apply for physics, but any other subject that you have to do SBA for. Social studies, history, geography, principles of business, and so on. As long as you have to do an SBA, you will have to analyze your data, interpret it, extract information from it, and make projection. Not only that, but understanding these principles at the foundation of statistics is a necessary or even crucial part of life skills, that you are not deceived by a one-sided argument using statistics. So as I said, we are here. The objective says Use standard deviation to compare sets of data. We have seen a little of this before, but now we will deal with it in detail. Also, the explanatory note here says no calculation of standard deviation will be required. So you are not required to calculate this for CSEC, but I will show you how to calculate it so you could understand it better. To begin with, we need to know what is standard deviation. And the syllabus does not give a definition for this. This is the part of the syllabus. Notice SQ and then SU. So standard deviation, ST, is missing. However, one way of stating what standard deviation is, and it is indicated by this symbol here, which is sigma, lowercase Greek letter, it is a measure of how dispersed the data is in relation to the mean. A low or small standard deviation indicates that data are clustered tightly around the mean, while a high or large standard deviation indicates that data are somewhat more spread out. Another way of stating that is a standard deviation is a measure of the spread of individual observations from the mean of a set of data. And still another way of stating what standard deviation is a standard deviation is a measure of how much your data scatters around the mean. An easier way to understand this is that the standard deviation is somewhat like the mean of the differences of the data points from the mean of the population. And right now you may be thinking, this looks harder. All right, I'll explain it. So let's consider some students here and their weight. We have some summary here, information from that, total, mean, median, range, first quartile, third quartile, interquartile, semi-interquartile range, and Q2, which is really the median. So let's take a closer look on the next slide. We will also briefly consider the formulae in Microsoft Excel that were used to get these measures, these calculations here. So these measures of central tendency and measures of dispersion, especially since some of you may not be taking information technology, but will need these for your SBAs. So, okay, that's our data. And this is the information that we extracted from the data. So how did we use Excel to get this? Well, first of all, we go to the ribbon on the top. We go to this sign here, which is uppercase sigma, and we click on this drop-down menu here, and we get this. We then scroll down here to statistical, and down here we scroll down to quartile. It's a built-in function. So we are going to insert that function where this 47 is to get that 47. So after I click on this OK here, this window comes up. It asks for the array. I highlight it or type it in, C3 to C17. I type in 1 here, meaning the first quartile. And even before I click on OK, it gives me the answer here as 47. And it says formula result 47. So once I click on that OK, it actually gives me this 47 in that space there. That was the formula for this first quartile. And so for the rest of them, say median, I type this in this position, and once I press enter, it says that the median is 60. And let's take average, where it's in that cell, I type in equal average, C3 to C17, and I press enter, and it says 60. So these are the formulae that will give those results up there, just in case anybody wants them. And by the way, when I complete these videos on CSEC mathematics, I will prepare other videos on the use of Microsoft Excel, including graphs, and those videos will be published in their entirety on YouTube, this same channel, for those who are not taking information technology, so that you can have the knowledge and skills to work on your SBAs more effectively and efficiently. But that is after I finish with this math. Now we have another parameter here, standard deviation. And remember, we are looking at standard deviation in this objective. So how did I get that standard deviation at this point? So I am on statistical, and I scroll down until I get here STDEV with a P, standard deviation. Now if I press OK, I'm going to find the standard deviation of all the data points that I entered in that table. Now P here means population. Your program, your Excel program, will consider everything as population, even though that may be a sample of your population. So now, once I click on OK, this comes up, and once I type in that C3 to C17, I have the recommended answer here, that it's 13.7, and here it even say formula result 13.7. Of course, once I click on OK, that 13.7 goes into that cell. This 13.7 fills that cell where the standard deviation is located. If you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. Okay, so we get the standard deviation as 13.7. We know how to calculate it using this Excel program. But what does that really mean? You understand what the rest of the stuff here mean, everything. What does standard deviation mean? Now, if I go on an online calculator, I'll get basically the same thing. This is the calculator I'm using here. I entered the data here and click on calculate, and this is what I get. Notice you have standard deviation, sigma, and corrected sample standard deviation, S, and they are slightly different. So you have standard deviation here, and so on. Now I am coming back to this absolute deviation and mean deviation. It says that the average, which is the mean, is 60, and the symbol it uses is this mu, which is the Greek lowercase letter m. And this here is the Greek lowercase letter s, sigma. So we take a closer look at this. Standard deviation, we got 13.7. If you treat all of these as your population, now if you treat that as your sample, the program will pick only a few from here and calculate your sample standard deviation, even though these weights may be sample of your population. As far as the program is concerned, this is your population. So standard deviation, sigma, is 13.7, corrected sample standard deviation, S. So this S here is our regular English S, and this here is a Greek lowercase letter s, sigma. is that. Now, notice here it says absolute deviation, which is 184, and the mean deviation is 12.3, more or less. Standard deviation 13.7, and corrected sample standard deviation 14.2, and some other things. This is just a part of what you will get on the online calculator. So for now, the standard deviation sigma is 13.7, and that is what we are concerned with right now. There are different types of standard deviation, as I just pointed out. The one we are interested in here is the population standard deviation, which has this symbol, sigma, which is a lowercase s in Greek, and which is all the data entered in the table, even if that table is just a sample of 15 from 300 students in XYZ school. As far as the program is concerned, that is all it has, and it will treat everything here as your population. So the standard deviation, population standard deviation. There is another one that says sample, which is SD, S, or SX. Now the program will choose a sample of your sample, which it calls the population, and gives a slightly larger answer, as you see down here and up here. So there are different types of standard deviation. This X bar is the mean for sample, and this mu, which is a lowercase m, is the Greek m, is the mean for population. So what does this mean? What does this 13.7 standard deviation mean? And how did they get that? Now, I know we could go online and calculate it. But what exactly was done to get that? So it's a little complicated. So bear with me here while I try to explain. And you may have already realized that we are using some Greek letters to represent certain quantities. Up here you have the uppercase Greek letters like alpha and omega, where the Bible talks about God referring to himself that I am the alpha and the omega. That's the uppercase letter. You also have lowercase alpha here and lowercase omega here. We are using this uppercase sigma, which is really S. That is what uppercase S looks like in Greek. Sigma. And it represents the sum of. We are using this lowercase s here, which is also sigma, and it represents standard deviation of a population. We also are using this letter here, which is mu, which is lowercase m in Greek, for the mean of a population. And of course, X bar we use for the mean of a sample. So we are using those, keep those in mind when you see them, what they mean. So let us consider this column here. If we subtract the mean from every one of these here, so 81 minus 60, we get 21, 79 minus 60, 19, and so on. 60 minus 60, we get 0. 50 minus 60, we get negative 10. 40 minus 60, we get negative 20. Remember, 60 is the mean. If we add all of those, we will get 0. So what about if we take the absolute value of those? Let's ignore the negative sign. So we come to this column here. And so there's 21 there. This that was negative 7 is now just 7. And this that was negative 20 is now 20. If we were to add all of these, we will get 184. We have seen that before. And if we were to divide that 184 by 15, because we have 15 such numbers or values, we get 12 12.3. We have also seen that before. Well, it is not 13.7 yet. So we can understand this better if we see it on a column graph. Remember, we are trying to get to 13.7. Where did that 13.7 come from? It's not wrong, but where did it come from? So let's put this on a column graph. We plot it. We have the mean here, which is that blue line. And if we consider this first column here, it is actually plus 21 above the mean, which is this. And the next one is plus 19, which is this, and so on. 60, of course, is exactly at 0, which is here. This 56 is -4, or 4 below the mean, and so on until you get to this 40 here, which is 20 below the mean. If we add those, as I said, you will get 0. But what about if we add the absolute values? That indicates absolute. If we add them up, we get 184. We divide by 15 because we have 15 values, and we get 12.3. We are not yet at 13.7, but we are getting there. Remember that online calculator we were just looking at? You had absolute deviation as 184, and you have mean deviation as 12.3, which is what we have down here. Now, this is easy to understand. If we find the mean of the differences, 184 divided by 15, we get 12.3. That's the mean of the differences from the mean of the individual values. And so we get this here. So it's 12.3 on either side of the mean. 12.3, so we are at 72.3 to 47.7 on either side of the mean. Now, this is easy to understand, and this is what really should have been the standard deviation. And on some YouTube videos, they will tell you that that is the standard deviation. Well, it is not. It should have been the standard deviation, but there were some problems. So instead, it is just considered as the mean deviation. So we find the mean of all the deviation. So these are the deviations we have here from the mean of the sample or the population, and then you add that up, divide by the number you have there, and you get 12.3. That is a mean deviation. It's the mean of all the deviation from the mean of the sample. Now, this mean deviation lost out from its rightful place of being called standard deviation, because these absolute values you see here, they are difficult to manipulate algebraically, very difficult. But you are still thinking, okay, so when and how did we get 13.7 as being the standard deviation? As I said, these absolute values here are difficult to manipulate algebraically. So what was done? The mathematician just decided they were going to ignore those and instead square these values. So that 21 squared become this, and this -16 squared become that. Notice the negative is gone. So once you square that, you will do something with it. Let's look at what was done as we consider this far right column. Actually, this is the formula that is used. It's not very difficult. So first of all, they take the difference and square it, which is this. So remember I said the absolute values give some problem. So let's go back to this, square it, and you get these values over here. So 49 is the square of -7, and 324 is the square of -18, and so on. Then they were all added. That sigma there, uppercase sigma, that E-looking symbol, it means sum of. So when we add up these differences, we get this. And then that was divided by the n, the number of values we have, which is 15, divide by 15, and we get 188.4. So the last thing that was done was to find the square root of that. The square root you see here. If you find the square root of that 188.4, you get 13.7. And that is how we get 13.7 as the standard deviation. So what we have here in this red box is the mean deviation. And that is easy to understand. What we have in this green outline here is the standard deviation. 13.7 above and beyond the mean. And this is the formula that was used to get the standard deviation. So it is from 73.7 to 46.3. From here to there. So the standard deviation is slightly greater than the mean deviation. As I said, the mean deviation is very easy to understand. The standard deviation is a little more difficult to understand. Suffice it to say, it is a little more than the mean deviation. And you are still wondering, a few of you may still be wondering, but why? Why couldn't we just use the mean deviation? What is wrong with the mean deviation of 12.3? It was easy to find and easy to understand. What is wrong with it? Two things. Recall I told you that these absolute values that we have here, that they are difficult to manipulate algebraically. That's the first problem. Using this is extremely difficult. And secondly, the simplest formula that gives the result close to the mean deviation is this formula here. And that's a simple formula. You look at it, you may say it looks complicated. So now you know it's extremely simple. So this is what we will use since it is the established standard. Hopefully, you now understand what standard deviation means. It's a number that is slightly greater than the mean deviation to make it convenient for everybody. So now you know where this came from. The formula listed below was used, this one here, S, lowercase s sigma, which is standard deviation for a population, and mu is the mean of the population, mu. And then this slightly different formula here is used for a sample. Keep in mind that you don't have to do any calculation of standard deviation for CSEC mathematics, but you may have to do it for your other SBAs when you analyze the data that you collected. And the textbooks that I recommend also show you how to calculate standard deviation of sample using grouped data and frequency. So all you need to know for this objective is if you are given 2 or more standard deviations, you need to say what that means in terms of the spread of the original data. So to continue, we now need to talk about a bell curve for normal distribution. Recall from a previous video, we looked at this. If you consider this red curve here, that is considered a bell curve. If you have a large set of data and you plot them on a graph like this, you will get that red curve. And it looks like a bell, upside down bell. So it's called a bell curve. Let's use the data that we have. We will not get a very good bell, but we can see what it looks like. We introduce a different concept here of normal distribution. So we will plot a graph with normal distribution on the y-axis and weight on the x-axis. And this is the graph we get. As I said, it's not a very nice bell curve. It's not a good bell curve because we only have 15 data points. If we had like 100 or 200 or 1,000, we'll get a nice smooth bell curve for a normal distribution. But we will work with this. The mean we said was 60. That is there. And the standard deviation we said was 13.7. So if you take 13.7, one standard deviation down, you arrive at 46.3, which will take us to this green line. So this piece in here is one standard deviation below the mean. And normally, for a large sample or population, that would make up 34.1% of the values you have. And then if we go the other direction, we plus 13.7, we arrive at 73.7, we get to this point here. So this section here now is one standard deviation higher than the mean, which is another 34.1%. We can see this better in the next slide, where a large sample was used. So it will look like this. The mean is here in the middle. Over on this side is one standard deviation. And over on this next side here is another standard deviation. And together, that would make up 68.3% of all the values of your data. If you take two standard deviation, we will add in this much here and that much here, the two standard deviation, and a third deviation will take in this piece here and that piece there. Now, anything that lies outside here is very far from the mean or out here. And so when you hear about outliers, that means data that lie far from the mean. Not in the first standard deviation, not within the second, not even within the third. So one standard deviation here, plus or minus. Two standard deviation takes in everything from here to there. And then three standard deviation, almost everything, 99.9%. A hypothetical example to further demonstrate what a bell curve looks like and what it means is this. Now you see this bell over here? That's why it is called a bell curve, because the shape of this curve looks like a bell. Not that it was invented or discovered or proposed by anybody by the name of Bell. It just looks like a bell. So it's called a bell curve. For a normal distribution, both sides are the same, symmetrical. Now, we said that standard deviation is a measure of how dispersed the data is in relation to the mean. If you have a small standard deviation, the data are clustered tightly around the mean. You have a large standard deviation, the data are more spread out from the mean. So if you have math test 1 that has a standard deviation of 5, and you have math test 2 that has a standard deviation of 10, then the scores for the test 2 are more spread out from the mean than for test 1. So let's go back and look at some data that we used before. Test 1 up here, that's this one here, and test 2 down here, that's this one over here. We will actually prepare bell curves. They wouldn't be very nice bell curve because we only have limited data, 25. So after we get this normal distribution function here, we now prepare a bell curve for test 1. which looks like this. That's the mean, which is 58.52, somewhere here. The standard deviation is 5.8. So 5.8 down this way and 5.8 up that way. This here is one standard deviation below and above the mean. So you can see that the marks are bunched up closer together, and the standard deviation is just about 6. If we had like lots of data points, that would make up 68.3% of all the values we have. So that was this one here. Let's look at this one over here. Straight off, you could see that the data points are spread out further. You have the mean here, which is 58.4, about there. And one standard deviation is 23 or so. So if we take one standard deviation down this way, we arrive to this point, somewhere here, and that is one standard deviation. Notice it is spread out much more than what we had up here. And then if you go the opposite direction, one standard deviation, we arrive at 81.46, which is here. So this is the other standard deviation. So that now that still makes up 68.3%, even though it is spread out much more. But because the standard deviation is higher, it spreads out more than if the standard deviation were low. So this is the one with 5.8, that one there. And this is the one with 23, this one here. So you could see with a larger standard deviation, the values spread out more around the mean. So as I said, a small standard deviation indicates that the data are clustered tightly around the mean, and a high standard deviation or large standard deviation indicates that the data are more spread out. So let us say in test 1, the standard deviation is 10. So from here, so that point there is 10, negative 10, and this point here is positive 10. So from here to here would actually be a difference of 20, but the standard deviation is 10. Another test, standard deviation is 5. So it may look like this. This point here is 5, negative 5. This point here is positive 5 in terms of standard deviation. And so from here to here spreads out a value of 10. But remember, the standard deviation is 5. And then if the standard deviation is 15, you may get something like this. So this is one standard deviation, which is 15 down this way. And this is another standard deviation, which is 15 up that way. So that this red line now, it still makes up 68.3% of the total data points. And I think that that should suffice for this objective. Now consider the 3 outlines of the bell curves for the 3 large samples given above. The x-axes have the same scale. So this is sample A, that's sample B, and this is sample C. The question is, which sample has the smallest standard deviation? And obviously, the answer to that is B, which is this one. And the reason for that is that from +1 to -1 standard deviation, the spread is the least about the mean. Now, assume the table below shows the standard deviations of the mathematics scores for grade 9 CCSLC in 5 Caribbean countries. Now, this is hypothetical. That's in Guyana, Trinidad and Tobago, Jamaica, Barbados, and Grenada. These are the standard deviations. In which country were the marks least spread out? Well, it would be this one, because that's the smallest standard deviation. So the answer is Guyana. Can you use your answer from one above to say that that country, Guyana, performed best in this mathematics test? Can you do that? No. You cannot use one piece of statistical information to draw a conclusion. So if the answer is no, as we said, what two other pieces of information you will need to help you answer this question here? And two of the most important are you need to know the mean and the interquartile range. And that will give you a better picture of how these countries performed in these tests. Could be that even this 10.7, that the marks are bunched together, that may not be as good as, let's say, this 20.5, where the marks are a little spread out, but the mean and the interquartile range are better for Grenada than for Guyana. It could be, or maybe not. So I hope that this helps. With this objective, use standard deviation, that you understand what standard deviation is, how it is calculated, though you don't need to do the calculation for this objective, and how to use it. So that's the objective. As I said, you don't have to know how to calculate it for this math class, but you may need to know how to calculate it for some other SBA. And that brings us to the end of video 11 based on objective 8 in section 5.